everyone and welcome back. In the last video, we explored embeddings and how embeddings actually convert into vectors and show us about the matching characteristics of words. And we also found that all the vectors that are directed in the same direction tend to have similar meanings or carry similar context. In the previous video, we also trained a model for a sarcastic dataset to find the level of sarcasm. But unfortunately, we had some overfitting and we tried various ways to overcome that overfitting. Like we tried L2 normalization, we tried to add some dropout layers and whatnot. Now let's see that how we can visualize those embeddings using a tool called Embedding Projector. It comes preloaded with many existing datasets, but in this section you'll see how to take the data from model you've just trained and visualize it using this tool. First, you'll need a function to reverse the word index. It currently has the word as token and key as value. So we need to invert it so that we have key as token and word as value. So using that, we just use a dictionary for that and find the word index.items. You'll also need to extract the weights of the vectors in the embeddings. So to get the weights is just a simple function called getWeights. So you print the weights shape. Then the output will be 2000 by 7. If you followed the optimizations in this chapter, we used a 2000 word vocabulary and 7 dimensions for embedding that we did to overcome overfitting. Then we just print reverse word index of 2 and weights of 2, and we find that the word new is given has the weights of the following. So the word new is represented by a vector with those 7 coefficients on its axis. So what does it mean? That this word new, what we reverse word indexed, is actually stored has a weight of 7 dimensions and is represented with this numbers 7 coefficient on its axis. The embedding projector uses 2 tab separated values called TSV files, one for the vector dimensions and one for metadata. So when we have to project, what is actually embedding projector? It's actually projecting our embeddings, but it needs 2 values that are 2 tab separated values called TSV files that we'll be generating now, and it has 2 files. One file contains the vector dimensions and the other file contains the metadata. This code will generate them for you. Import io, then out underscore v, io.open. So we are opening the vecs.tsv file that is in the write mode and we encode it with UTF-8. Similarly, we open for metadata, we call that file meta.tsv and we write into it. And what we write into it is for word underscore num in range 1 to cap size, word equals reverse word index of word num, then embeddings equals weights of word num, and we write this all down in out m and out v that actually writes into meta file and the other cap file. Then we close both the files, and if you are using Google Colab, you can download these files using this small piece of code which carries files.download, vecs.tsv and meta.tsv. Once you have them, you can press load button on the projector to visualize the embeddings as shown. So the embeddings would look something like this. You can just go online on Google and type embedding projector and you will be relocated to this page where you can see this load button. You have to load both the files vecs and meta file and you'll see something like the dot structures you can see on the right hand side of the image. This will cause the words to be clustered on a sphere and will give you a clear visualization of a binary nature of the classifier. So once it's loaded, you will see something like this. You will see a cluster of dots, as you can see in this photo, the visualization of sarcasm embeddings, right? Screenshots don't do justice, so try it for yourself. Then using pre-trained embedding from TensorFlow Hub. What is that? Is till now we were just writing the embedding line of code in a model by ourselves. What if we have a pre-trained embedding that we can just get from TensorFlow Hub and use as it is in our whole model and not write it on our own, right? And it is actually pre-trained on more data set than we have, so it might affect our own model and it might reduce overfitting that we were not able to do in the previous thing. So as an alternative to training, your own embeddings is to use ones that have been pre-trained and packaged into Keras layers for you. There are many of these on TensorFlow Hub that you can explore. One thing to note is that they can also contain tokenization logic for you. So you don't have to handle all the tokenization, sequencing and padding. It's already done for you. So TensorFlow Hub is pre-installed on Google Colab, so you can just call it and use it. Otherwise, just use pip install to install that. For example, with sarcasm data, instead of all the logic for tokenization, vocab management, sequencing, padding, etc., you could just do something like this. Once you have your full set of sentences and labels, first split them into training and test sets. So that we've already done. We used 24,000 training size at 24,000 and the rest goes into the test set from 26,000. Then we divided the training sentences and the testing. Similarly, we divided the training and the testing labels. Once we are done, we download a pre-trained layer. So it's nothing, just a small code. So we have imported TensorFlow Hub as TensorFlow as hub, and then hub layer equals hub.keras layer. So we are defining which layer we want, and this is a simple code for URL, so you can get that and just input the output shape to be 20 in the input shape as it is, and the type is string and trainable equals false, because we don't want it to train along with our model. We want the weights that it has been trained upon previously. This takes the embeddings from Spill dataset trained on 130 GB of Google News. Using this layer, will encode our sentences, tokenize them, and use words from them with a single embedding, with embeddings learned from the part of Spill, and then encode your sentences into a single embedding. It's worth remembering that final part. The technique we've been using to date is to just use the word embedding and classify the content based on all of them. Right? When using a layer like this, you're getting the full sentence aggregated into a new encoding. So earlier what we were doing is we were going word by word, but now using this layer we are going sentence by sentence into encoding. Right? So the next thing is just as it, you define the model and you just have that hub layer inside. In the first layer only, you can see you have the hub layer, and then the last and the second last is just a simple dense layer. Adam optimizer similar as previous, and model.compile is similar as previous. This model will rapidly reach peak accuracy in training and will not overfit as much as we saw previously. The accuracy over 50 epochs showed training and validation very much in step with each other. So you can see that the accuracy for validation and for training is almost the same and it's fitting nicely. So loss values are also in step. Similarly, you can say the loss is also decreasing for validation as far as for accuracy. It is worth noting, however, that overall accuracy is quite low, considering a coin flip would have 50% of the chance. So we'll see that overall accuracy will come out to be around 67%. But of course, a coin flip also has a probability of 50% of getting it right? So this is caused by encoding of all the word-based embeddings into a sentence-based one. In the case of sarcastic headlines, it appears that individual words can have a huge effect on classification. So while using a pre-trained embeddings can make for them much faster training, less overfitting, and you should also understand what it is that they are useful for and that they may not always be the best for your scenario. So in this chapter, we built our first model to understand sentiment in text. We did it by taking the tokenized text from chapter 5 and mapping it into vectors. Then using back propagation, it learned the appropriate direction for each vector based on the label for the sentence containing it. Finally, it was able to use all the vectors for a collection of words to build up an idea of sentiments within the sentence. You also explored ways to optimize your model to avoid overfitting and saw a neat visualization of the final vectors representing your words. While this was a nice way to classify sentences, it simply treated each sentence as a bunch of words. There are no inherent sequence involved, and as the order of appearance of words is very important in determining the real meaning of the sentence, it's a good idea to see if we can improve a model by taking sequence into account. So, next we'll be learning about recurrent layer, or that will form a foundation for recurrent neural network, where we'll actually go into the context of what the sentence is about and how the words are in context with each other. Also, we'll see another pre-trained embedding called Globe, which all allows you to use word-based embeddings in transfer learning scenario. So let's get started with that in the next video. But for now, let's just jump to the code and understand how we can conclude this chapter with all the things that we have learned till now. So here is our code for visualizing the embeddings with embedding projector. So step 1 is to reverse the word index, as we have already read that we will be reversing where the word is represented by the token and the key is represented by the value. So we are using a dictionary operation where we are reversing this order. Then we use get underscore weights function to get the weights of the model layer. Finally, we print the reverse word index and weights of the second number. And also for using embedding projector, we have already read that we require two values of called the two tab separated value file called the TSV files, which we have two files. One is the vector dimensions file and one is the metadata file. So you can see we have opening the vecs.tsv file in reading mode, in writing mode, and the same meta.tsv file in the writing mode. Then we write down the words index and weights of the numbers into that, and then we close them. Finally, we download these files, vecs.tsv and meta.tsv, and then we just load them to the projector. Now, for using a pre-trained embedding, we have the similar thing only. This whole code is the same as before. We have already seen that, so I'm skipping through it. But from here, we are importing Tensorflow Hub because that layer is in Tensorflow Hub, hosted in Tensorflow Hub. This is the link for the Tensorflow Hub for civil dataset. So hub.keras layer to get that layer. Output shape is 20, input shape is we don't know yet, and then tf.string and trainable equals false, right? Then we just add that layer into our model like this, and the rest of the things go same. Model.summary, we can see it has 40020 parameters, just the Keras layer itself. That is, it has so many parameters, means it is trained on a much bigger data set, right? Then number of epochs we set to 50, and then we just train it, and to my surprise the accuracy was just around 66% for 50 epochs. So the training accuracy was 66% while the validation was 65. That is close enough, so we can't actually say that it's overfitting, right? So you can see, when we map that out, we can see the validation accuracy and the training accuracy and how they are with each other. It's a bit jiggly, but we can almost smooth that out. And similar for the validation and the accuracy loss. When we test out sentences like these that we did in the previous one, we can see the predictions of 0.5221, and that means it has the higher probability that it is a sarcastic headlines, right? While the other ones have a lower probability. So that's all for this code and chapter number 6. We are done with that. In chapter 7, we'll be understanding recurrent neural networks or RNNs and how we can use them for understanding sentiment analysis. And you can find all this code in our GitHub. The link would be in the description. If you have any doubts, any comments, do send in the comment section or on our Twitter handle. Thank you so much for joining in, and see you in the next class.